Good morning, everybody. Today I'm going to be talking about Codeforces round 659. It was a Div 1, Div 2 round. I competed in Div 1. I did all right, not super great, but okay. And I'm going to talk about the solution videos to all the problems now, or all the problems I solved at least, which will be Div 2, A, B, C, and D, and then maybe, well, let's just look here. Div 2, A, B, B2, C, and D, and then also Div 1E. I have a solution idea too. So I didn't finish coding Div 1E, but I know how to do the rest of these. Okay, so for this first problem, you have some array of strings. You don't actually know what that array is. You have to generate it. And you need to make it in such a way that the common prefix array between every adjacent string is something that they tell you in the problem. So namely, it's something like this. So you'll have like some string here. You don't really know what it is. And then you'll have some other string here maybe. And then you have some other string here. And they tell you the first time these two are different. So the first index, they're different. Maybe it's this index here. And maybe the first index these two are different is this index here. So to actually implement this, what you can do is you can make all of these just be all A's. So this can be an A all the way across. Then you can make these all A's as well. But then this first index, they need to be different. So you can just change it from an A to a B. And then you can make the rest just the same as the top line. Now in this third line, you want this prefix to match. So you just copy the string originally, make these all the same. And now you want them to be different here. So now instead of just making this character an A, you would make it a B. That way it's different. So you can do this using all characters A and B. You don't have to worry about running out of different characters to use. And you'll get the longest common prefix array because you'll find mismatches in exactly the positions that they are looking for. Awesome, so that's Div 2A. Div 2B was a little bit more tricky. It had a sub-problem, so there were like two versions of it. And I think I want to talk about the hard version because that's kind of the slightly more interesting one, in my opinion. So my understanding of the problem, I didn't actually solve it, so I could be misunderstanding, but you've got some shore here. So this is the shore, and then this is the island. And then between these, you have like some water. And the water might go something like this maybe, or the floor of the ocean, I guess. So now the ocean is initially like this, but then it goes up and down over time. So the height of the ocean, it'll initially be some small value, or it'll be 0, and then it'll increase to this height here, and then it'll decrease to the same height here, and then it'll just repeat. So you're comfortable swimming only in ocean levels that are like only if the depth is a certain amount or less. So in this case, it's okay to swim here because the depth is this other value, but it's not okay to swim swim in this position because it's too deep. What you can do in order to handle this is you can think about like you're only capable of walking on land, and you can just imagine the ocean is a little bit deeper than it starts out. In my opinion, I think that's a lot easier to think about because then you're not like imagining a dotted line underneath the water. It's just like the level of the water is where you're allowed to walk. So we'll like imagine like moving the entire land up by however deep the ocean is. So like maybe this is like where the ocean is now. So now this moves up and then it moves down, but it should be pretty clear that if there are any positions that are below the lowest the ocean ever gets, it's going to be impossible. So we'll say for simplicity, maybe the ocean is here instead. And it's going to move up to maybe it moves up to here, and then it moves back down to its position as well. So there's like the upper and lower limits of how high the ocean gets. Now, there are certain positions here that we'll always be able to swim on. In this position, for example, no matter where the tide is, it's safe for us to be there. So we can get here, and then we can like maybe take a rest and wait for the tide to go up, and then wait for it to go down again. So what we can do is we can actually consider this sub-problem here as just a completely independent problem from this problem here. We just want to know, can we solve this left one? Can we solve this right one? every time you have one of these instances in which this is higher than the tide ever gets, we can ignore the dependence between the two sides of it, because we can just wait as long as we want in this position here. We'll always be able to swim there. Awesome. So we can split it up, and now the only problem we have to solve is for this smaller range, can we solve that? In this case, well, it depends how quickly the tide moves, I guess. But what you can do is you can say for this position, which position I guess are we interested in? For this position, there's a certain time range you're allowed to be in it. So you can be in it in like, maybe this is like the height of the ocean, right? So the ocean goes up and then it goes down. The time that you're allowed to be in this time range is whenever the ocean is below that level. So it's going to be this continuous time range here. Or you can also think about it as what time can you not be here, and that'll be this range here. So for each different x coordinate, we'll have one of those ranges. Here's the time that you're not allowed to be in this position. Now, very good. But the issue is, like, it's not really clear how we should move. So what we can do is we can notice it only makes sense for us to just do a straight, like, swim straight across for all positions that aren't ones that we're safe at. Because in all of these positions, if we wait until the tide gets as high as possible, then we've created an issue, right? Like, it's gonna be, we're gonna drown. So instead, what we can do is we know we want to like swim across when the tide is as low as possible, and that's where we want to just keep going forward. And if we would want to like swim across and then wait, the only reason we'd want to wait is because the tide is going down. If it's going down, we could have just started later. So basically what we can do is we can convert each of these positions to, or each of these like ranges of times we're allowed to be here, to a time that we're allowed to start. And we can do that just by shifting it back a certain number of time units. So instead of saying you're allowed to be at this position at times blah blah blah, like A, B, and C, instead we'll say you're allowed to start at times A minus whatever, B minus whatever, and C minus whatever. So now you just want to say, okay, you've got a bunch of these ranges, and you want to say what is the union of these ranges. So these are all the times you're allowed to be in it, right? All the times you're allowed to start. You want to say, when are you allowed to start? And if you start at this time, you'll be able to clear all of the different positions. So you just take the maximum of the left endpoints and the minimum of the right endpoints, and then you'll get this range here. And now if this left endpoint is like comes before the right endpoint, that means you can start anytime in this range. But if you have something that looks like this instead, maybe you have this range here, this range here, and this range here, this will be your right endpoint, and this will be your left endpoint. So there will be no place you're allowed to start because the range will be empty. Okay, so that's problem B. All of the things that we did here didn't rely on the size of the numbers. We just looked at, like, we just did some math for the size of k. We didn't actually iterate through anything that had anything to do with the height or the length of the like period of the ocean. So all of this can work for the harder version as well, because it's just based on like just operations and just which numbers are greater and less than which other numbers. Awesome. So that's problem B. Let's move on to the Div 1 problems now. Div 1 problem A is the string transformations problem. So this was pretty straightforward, I thought. The idea behind it was you have like some, or the problem statement, I guess, was you have some string like this and maybe some string like this. And, oops, BBC. On a given, no, it's BCC, rather. On a given turn, what you can do is you can take any number of characters in the first string, you select all of them, and you can increase them to any other letter. So you can only move them back in the array, or in the alphabet. And yeah, so how do we do that? In this case, what we can do in order to do it in the fewest number of operations, so we can turn these two A's into B's, and then we would have B, B, B. Then we can turn these last two B's into C's, and then we have B, C, C. So one thing to notice is occasionally we can like double up our operations. If we did this naively, we would just do A to B, and then we'd have to do A to C, and we would do B to C as well. Now this is kind of slow, because what we could do is we could have this A come along for the ride and turn it into a B, and now we have this extra B, but we've just merged these two operations into one. So like the observation that you can make here is you always want to, if you can like merge two elements, that's always a good thing to do, especially if you can do it for free, right? If you can merge the A's into the B's for free, you always want to do that. So if we're going to be turning an A into a B, we might as well just turn all of the A's into the B's, because it's possible that we gain something from that. Like in this case, it's possible it doesn't matter, but if it doesn't matter, then we could just, all of the operations we would have done with the A's, we just do them with B's now instead. So it doesn't make it any worse. The other thing to notice is whatever the smallest letter is that's still alive, or that we still want to get rid of, that's a good letter to do an operation on first. So here, the smallest letter we want to get rid of is this A. It's smart for us to change the A first, because we know if we wait later to change this A, it won't get any better. It's only going to get, like, well, it won't get any worse either, but any cost that we have to pay in order to change this A, we're not going to decrease that cost by letting something else turn into A, because things only get bigger. So since it only gets bigger, we can take whatever the smallest one is and do something with that first. So we can turn this A into a B. Then we can, later on, we'll have these B's, B, B, B. And we need to turn it into B, C, C. So we'll say, okay, well, these B's we can ignore because they are whatever they want to be. So we can just like imagine deleting them from the array. Now these ones we need to turn into C's. So we can do that now. So repeatedly, what you need to do is find the smallest like letter that needs to be changed, unhappy letter, and you want to make it happy, turn it into the letter that it wants to be. And you do that for all letters that match that smallest letter. Okay, so yeah, that's pretty much the entirety of the problem. In order to make it faster, you don't actually care, you don't need the array to be a very big array. You only care about unique copies of each letter. So there are only, there you go, that's how you do it. There aren't that many types of, oh, maybe there are a lot, never mind. But there are only like 26 by 26 different possible inputs, or different possible, not different possible inputs, different types of like letters. And if you have two A's and both of them want to eventually turn into B's, then you can just imagine merging these into the same letter. So if you do that, your runtime is like the number of test cases times 26 squared, which is, this is like at most 10. So this will run very fast. Plus like enough time to read an input. That's pretty trivial. All right, very cool. So the other problem I'd like to talk about is this D1D. In this problem, you have a bunch of numbers. So maybe you've got like 3, 7, 5, 3, 7, 5, 1, I guess. Or maybe 1, 1, 2, like that. So if we write these numbers in binary, it's more helpful. This will be 0, 1, 1. This will be 1, 1, 1. This will be 1, 0, 1. This will be 0, 0, 1. And this will be 0, 1, 0. Now, you've got two players playing this game. On a turn, each player picks some number and deletes it. But they change their score, or like they kind of like take the number. But your score is the XOR of all of the numbers you take. And you want your XOR to be as big as possible. Yeah, that's the game. And the question is, who wins, the first player or the second player, or do they tie? So there are a couple observations to see here. The first one is that any bit that occurs an even number of times doesn't matter. So in this case, this bit here occurs an even number of times. What that means is either both players have it or neither players have it in their XOR. You only have it in your XOR if you have picked an odd number of them. So if we have two numbers like A plus B, and they need to be some number that's even, right? So A is the number of things the first player takes that have this bit on, B is the number the second player takes that have this on. If together those need to be an even number, that means either A is even and B is even, in which case they're both 0, or A is odd and B is odd. So either they both have it or neither do. And the opposite is true as well. If there are an odd number of those numbers, that means exactly one player needs to get points for it. So all we care about are the bits that have an odd number of occurrences. And we also only care about times where the bit that has the odd number of occurrences is the biggest bit. If we have a smaller bit that has an odd number of occurrences, it doesn't matter, because no matter what the score is for those numbers, it's only the score for the biggest power of 2 that will determine the winner. Cool. So how do we do this biggest power of 2 thing? Well, we just look through each bit and we see, okay, which one occurs an odd number of times. So let's do it. The first bit we've just seen occurs twice. That's even. We don't care. Second bit occurs here, here, and here. So the second bit occurs 3 times, which means the winner is going to be determined by whichever of the 2 players has a 1 in their second bit. So that's what we care about. And since we only care about that, the only thing that matters is whether these have a 1 in that column or a 0 in that column. So we can change the array to just 3 1s and 3 0s. Now, you want to be the person who takes this an odd number of times. This is like kind of an interesting case. Let's first look at the case in which you have just 1 1. So maybe this is the array. There's only 1 1. You want to be the one to take it, because that means you'll have the total. So if there's just 1, this is like number of 1s. There's just 1, that means you win. If they're an even number, it doesn't matter. So let's look at 3. Well, 3 is an interesting case. If you have exactly 3 1s, like this, then whoever goes first ends up losing, because they'll take this. This will be like Alice takes this. Bob takes the next one, and then Alice has to take the third one, which means Alice has taken an even number, so it doesn't count in her XOR. But it does for Bob. So if you take 3, you might end up losing. But it turns out you can also win in some cases, and this is what I didn't see in my first wrong answer. It's also not in samples, surprisingly. So if you have like a 0 here, what Alice can do is Alice can take the 0, and now Alice is player 2 in this game. So that's kind of the important part. We have company. Understood, sir. Which means like the number of zeros here, each time you have a 0, a player will want to take it in order to flip the parity of what happens. Excuse me. Yeah. So what we do here is we just count the parity of zeros. Now you might ask, what if the opponent takes a 1 instead? Like, we're assuming they're going to take zeros. What if they take a 1 instead? Well, if they take a 1, then we can also take a 1. And now if we take a 1, whoever takes this 1 loses. So it's the same thing. Like if you play optimally and you're going to win, you won't let them take all 3 1s. If they take 1 1, you take the other, and now they're going to be forced to take the last one. Okay, cool. So yeah, so that's what happens when you have 1 and 3. Now the next case is, what if you have 5? Because 5 is also an odd number. Well, if you have 5 1s, and maybe some 0s as well, you can imagine combining these 2 together and also combining these 2 together. When you do that, what happens is, if one player takes this one, then you can respond by taking this one here. So anytime one of them is taken, the other one's also taken, which means basically for every pair that we have, we can just delete this entire pair. Now we're left with these just one thing or just 3 things. This is true for groups of 4, right? When you take a group of 4, if you take 2 of them and your opponent takes 2, the entire thing cancels out. It's not true for groups of 2, because if both of you take 1, then you flip the parity of like whether you want to take a 1 or whether you don't. So essentially, since we can ignore any group of 4, the only cases that are relevant are the 1 and the 3. The 5 is just the same case as the 1. And if we have a 7, that's also just the same case as a 3. So overview of how to solve the problem. You find the highest 1 bit that occurs an odd number of times. That will determine who wins. Whoever gets that 1 bit wins. So now you're playing a game with 0s and 1s, and you want to be the person who takes a 1 an odd number of times. If the number of 1s left mod 4 is equal to 1, that means you can win. You'll take the first one, and now you can copy your opponent. If it's equal to 3, you care about the parity of the number of zeros. So if the parity of the number of zeros is even, that means basically there are no zeros, which means you have to take 3 ones and you're going to lose. Or you have to take 2 ones, you're going to lose. Your opponent will get to take 1. If the parity is equal to, or if the value mod 4 is equal to 1, then you take the first one, and now you win no matter what, because you copy. If the parity of zeros is odd, then you take one of the zeros, and then you'll be the one, like now the parity of zeros is even, so you can delete the rest of the zeros, imagine them deleted, and now you'll be the person who takes the leftover one, so you'll win. Or you'll be the one who doesn't take the leftover one, rather, so you'll win. Okay, yeah, you get the point. The last problem that I think I know how to do is this problem E. And I'll kind of give a brief description of how to solve it. I ran out of time when trying to solve it myself. So, yeah, kind of unfortunate, but we'll see. So the idea behind this problem is you've got some string, and in a given move, you can delete either a 0, or if you have 2 ones next to each other, you can replace it with just 1 1. So if your string looks like this, you could maybe delete this 0 if you want, or you could replace this 1, these 2 ones with just 1 1, so you could have this. You can also, if you, well, yeah, I guess those are the only 2 moves. Delete a 0 or replace 2 ones with just 1 1. Now the question is, how many different strings can you reach? So in order to solve this, basically, you can do a DP, where your state is like DP at which one you're at. And then between doing these ones, what you can do is you can try and place some number of zeros. So your transition is like place any number of zeros. And then after you do this transition, you take the first one after that. So if you place like some number of zeros, then you have to take the one like immediately after. And you can kind of think about this equivalently as like ending with a 1. So if you add a 1 to the end of your string and you're forced to end with that 1, then that will like probably make it easier to implement, I think, according to this idea. There might be a completely different way of doing it. The issue is this is like an order n state, and this is also an order n transition. So it's tricky to do both of these because we don't want our runtime to be n squared. So what we can notice is the next one that we'll look at, we want to find the first one that's available after we place a run of that many zeros. So maybe an interesting case for this would be something that looks like this string. So 1 1 0 0 1 0 1 0 0 0 0 1. So now let's say we're at this one here, which presumably means we've already placed like 2 ones or something. After this, if we want to place like 1 0 and then follow that by a 1, then we want to place it from here. Because if we place a 0 and a 1, that means we want to be here. Now, we could place this 0 and this 1, but we don't want to double count placing a 0 and a 1. So we'll like count it by the earliest time we could place that. So this is where our DP will go to. But we would also use this group if we place 2 zeros and a 1. It's possible that the next thing we place would be 3 zeros and a 1, because we could delete these 2 zeros, and then we could delete these 2 1s, or we could delete this 1 since it's next to this one, and we could delete these, and then we could delete this, and now we have 3 zeros and a 1. And that works. But if we do that, then the next one we go to shouldn't be this one, it should be this one, and that would be the next one in the array. Okay, so yeah, that's fine. The issue is this is a bit tricky because we don't know where our next DP state is going to be. It's kind of unpredictable. So what we can do is we can notice the places that we would go form like a monotonic chain. So here we have a group of 4. Before that, we'll have a group of 2. Maybe before that, we have a group of 1. So basically what this looks like is you've got this chain here, right? Maybe you've got that there, that there, that there. This forms like an increasing stack. So you can keep this in a stack, and then if you read some new value like this, you can keep removing from the stack until you have increasing values. And these will be the only DP states that you'll wind up hitting. Now what you can do from here is you can, like, you want to sum up like this DP state plus these two DP states plus these DP states plus these DP states maybe. And you want to like add each of them into your total, and you want to find that sum so that you can very quickly do your transition. But you want to do that faster than linear time. The thing to notice is you can pre-compute, like if you start here, or not, you're not really pre-computing, you're doing it in the DP, but you can say if you start here, what is the sum of this total? And we can also store this sum here and this sum here. And it's very easy to do. We just look at these two values plus whatever this value is here, which we've already computed in our DP. So now if we want to calculate it for this value, we can do the same thing. We can calculate this entire sum. And that's just going to be these values plus this next thing here. So now when we add some new value to the DP, like maybe we add this thing here, we would need to remove this from our stack. And now we need to change this value. It used to be too tall. Maybe this is just one position now. And now the other position would be from here. So we can modify it and recalculate this value. But in order to recalculate this value, we just need to look at the one value after it. So that's why this recalculation is just order 1, amortized. You might have to remove a bunch of stuff from the stack, but you only remove something from the stack once. Okay, awesome. So yeah, those are all the problems I know how to do. I don't know how to do the hard version of this problem. I spent a bunch of time trying to like do meet in the middle stuff, trying to do like a traveling salesman sort of DP with a factor of n removed from it, but it's tricky. There are some cases, I guess, that were a bit difficult to handle, so I didn't actually wind up coding it. I was also very afraid of the time limit. The 10 test cases part scared me quite a bit, so yeah, I didn't actually work on it too much in contest. And then problem D, I didn't spend, well, I spent a little bit of time on, but like I wasn't able to make any concrete observations. I just had like, well, maybe this is the right thing to do, but also maybe it's not. And I couldn't prove anything, so I'm like, there's a good chance that if I go down this path, I'll just like not actually solve the problem. I'll just get wrong answer and not know why. So yeah, that was my contest. Performance-wise, I was kind of happy with how I did. I ended up beating William Lin. So there's that. Most people didn't see that coming. Oh, I tied with him even. Look at that. My name comes first. That's the real strat. So yeah, I tied with William. Good job to him, I guess. I guess he's probably not at all happy with his performance. I could have done better for sure, but oh well. Eric To got E. Good job to him. And then the LGMs did kind of how you would expect. Tourist got second, but thankfully he gained some rating, which means I don't think the rating jumps are in yet, right? Or maybe it is. It is in. Okay. So he's 3-7. There we go. Back on top. Thank you, Tourist. Well done. The king returns. He's also just like 4 points away from the highest he ever was, which is very impressive. All right, that's all from me. Hope you enjoyed the problem review. I will also post my screenshot or screen share and like some commentary as well. But I have to remove part of that, so I have to do a little bit of editing because afterwards I tried to do a problem review on it, but it was on the wrong screen, so like it didn't record very well, and it wouldn't have been very interesting to watch. Hope your rating went up. Hope you enjoyed the contest as much as I did. Thank you for watching, and goodbye.